Okay, in this video, we're going to be talking about all the different types of numbers that we're going to be working with in this course. And we're going to start out by defining each of them. And every one of these numbers we're going to be talking about are real numbers. Later on, we'll be talking about another type of numbers, but for today, we're going to be dealing with all the real numbers. The real numbers, abbreviation, capital R. Okay, the real numbers consist of the following sets of numbers. So if you have a real number, first off, it's either going to be irrational or it's going to be rational. It can't be anything else besides irrational or rational. And irrational numbers are numbers in which the decimal form never terminates or stops and does not repeat. So common examples are pi. That's probably your most common example of an irrational number. And non-perfect square roots. And it's very important that you know that stuff like the square root of 3, that's not a perfect square root. You can't just come up with that in your head. That's going to be an irrational number, meaning that it continues on. There's no pattern to its decimal. There's no repeating decimal. There's no pattern at all. So those are irrational numbers. Now, the opposite of irrational, again, the prefix IR means not. So the word irrational actually means not rational. So it's either not rational or it is rational. So it's got to be one or the other. It can't be both. It can't be anything else besides those. Rational numbers are numbers in which the decimal form either terminates or repeats. Example of what we mean by terminates would be like 3.47, to where there's nothing else after it. It stops after the 7. So that'd be a terminating decimal. A repeating decimal would be something like 3.4 repeating. Or it could be 4.573, and all 5, 7, and 3, the whole thing might repeat. But those are your rational numbers. So again, reminder of what I just said. Everything's either going to be rational or irrational. So anything that doesn't fall into this category is going to be an irrational number. Rational numbers can always be written as a fraction, very important. And that's actually where it gets its name, rational, because if you look at the root of rational, it is ratio. There we go. The root of rational is ratio, which is like a fraction. So anything that can be written as a fraction is a rational number, where a and b are integers. Now, if something is rational, we have some subsets here. So if something is rational, it could also be an integer, it could be a whole number, it could be a natural numbers, and you have some examples of each of these. Your integers are your positives and negative whole numbers, meaning there's no fraction or decimal parts. You have positive 1, positive 2, positive 3, 0, negative 1, negative 2, negative 3, and the dots here tells you that those sets go on forever. Your whole numbers are the same values, except for we're going to scratch the negatives, and that's going to be your whole numbers. A good way to remember it is your whole numbers start with a hole, like 0. And when I say hole, I mean like hole in the ground hole. It looks like a hole. So your whole numbers start with 0, and it goes 1, 2, 3, 4. Your natural numbers, actually sometimes called counting numbers. When you first learn to count, you learn to count natural numbers. More than likely, you didn't start with 0 when you first started learning to count. So your natural numbers, also known as your counting numbers, are 1, 2, 3, 4, 5, and so on and so forth. Organizing these. Now, I didn't like the diagram here, so I actually found a replacement for it. And the reason I didn't like this diagram is this diagram had your irrational numbers here and your rational numbers here. And there's a problem with that, because my question was, what's out here? What's in this space? Because you either have to be rational or you have to be irrational. There's no in between. So therefore, I found this diagram, like I said, that I liked a little bit better, because with this diagram, and let me erase my markings here. So hopefully you notice with this diagram, notice that you're either rational or you're irrational. Right there is the division. So everything representing this diagram is your real numbers. So your real numbers are first divided into rational or irrational. Then inside of your rationals, you could have integers is a subset. Now, could something be a rational number but not an integer? Sure, like 2.3. That's a terminating decimal, but it's not an integer. Now, entirely inside these integers, you have your whole numbers. Because, well, what numbers are outside here? Stuff like -3. Well, that's an integer, but it's not inside the whole numbers. The whole numbers are 0 through whatever, starting with 0, and it's your wholes. Your natural numbers, they do not include 0, so that's the only thing it doesn't include, but it has everything else out of there. Now let's talk about all the different abbreviations. How do we abbreviate rational, irrational integers? Here they are. The abbreviation for irrational numbers is the letter I. And when this is going to pose some problems because you can't then use I for integers. So you have I stands for irrational, Q for rational, and I always think of the word quotient. It starts with Q, and a rational number is anything that can be written as a quotient. Integers is the letter Z, whole numbers is a W, and natural numbers is N. Some examples again of each of those. Irrational numbers, examples was like pi, the square root of 3, the square root of 2, the square root of 5, any number that you don't know the square root of, any square root that's going to be a decimal. And I'm going to go ahead and throw in another one that we'll talk about later on, the value of E. E is going to be like a value for pi. It's like an irrational value like pi, but we'll discuss it later on in Algebra 2. Rationals, your rational numbers are any terminating or repeating decimal like 0.3 was rational, 4.5 repeating, 7/8 is rational, negative 5 1/4 would be rational because again any value that can be written as a fraction or as a decimal that does not continue on without pattern, all of those would be rational numbers. Even your whole numbers like 0, those are rational values. So any of these below, all three of these are actually rationals. These are subgroups. And again, the integers, we listed them above. That'd be like -3, -2, -1, 0, 1, 2, 3. It goes on forever in both directions. Your whole numbers start at 0 and continue on. Your natural numbers start at 1 and continue on. Okay, so that's all your different ones. Practice, let's name all the sets to which each belong. First off, every one of these values should be real. And then we go from real to is it rational or is it irrational? So this one is real. It is also rational because, well, you could write it as a fraction. You could do -10/1. So anything that can be written as a fraction or anything that doesn't have crazy. Another way you could think of that, the word irrational actually means crazy. And if you have like a crazy decimal like pi, we know that pi is crazy, there's no pattern to it, then it's going to be an irrational. So this is going to be real, it's going to be rational. It is also an integer. It is not a whole number, and it is not a natural number, so that would be it. Square root of 30, first off, is real. Since we don't know the square root of 30, we know that it's going to be an irrational, crazy decimal, so it is real and irrational. 1 7/9 is also real. It is obviously rational because we can write it as a quotient. It is not an integer because you have that fractional part to it. It's not a whole number. It's not a natural number. So we're done. Now, first off, on 24/8, please write that as 3. 24 divided by 8 is 3. So it is a real number. It can be written as a quotient. It is rational, therefore. It is an integer. It is a whole number, and it is also a natural number. It's all of the above. So there you go. 2.48 is real. It is obviously a rational number, and you might be saying, but that's a decimal. And once again, we could write it as a fraction, though. If you don't remember how to write a decimal as a fraction, this would be 2 wholes. And this right here, that's if you read this correctly, that's the tenths and hundredths place. So this is 48 hundredths, and you could reduce it from there. So it can be written as a fraction. So that is real, rational. However, it's not an integer because you have the decimal part. -√81 is the same thing as -9. So therefore you have real and rational. That is an integer, but it is not a whole number or a natural number. Pi minus pi, anything minus itself is 0. So therefore that's a real number and it is a rational number because it can be written as a quotient. It is an integer. It is a whole number because whole numbers start with 0. However, it's not a natural number because natural numbers start at 1. The square root of 16 over 25. Now, if you don't know how to take the square root of a fraction, you can actually just square root the top. Square root of 16 is 4. Square at the bottom, you get 5. So this is 4/5. 4/5 is a real number. It is obviously a quotient because that's what that fraction bar does, is division. So it's a real number. It's also a rational number. However, since it is a fractional part, it's nothing else. Point 15, repeating, is a real number. Since it is repeating, any decimal, it goes on forever, but it is a repeating decimal, so therefore it can be written as a quotient. Now this is, if you've never seen the trick for writing a repeating decimal as a quotient, here it is, just extra information. This is in the tenths, hundredths, so that's 15 hundredths if it didn't have the bar. Since it does have the bar, you can just take one away from the bottom, and you can write this as 15/99ths and reduce it, and that would be the ratio. That would be the fractional version of that. So this is real, it is rational, and since it is a fractional part, it is none of the rest of them. 109 is real, rational. It is an integer. It's a whole number because it starts at 0 and all the wholes, and it is also a counting number. So it is a natural number as well. -8/3 is real and rational. And since it's a fraction, it's nothing else because the integers, wholes, and naturals are have no fractional parts. Anything divided by itself is 1. So therefore, this would be real, rational. It is an integer. It is a whole number, and it is also a natural number. Okay, next up, let's talk about some properties. Properties of real numbers, and you've probably seen these properties before, but let's go over them again. The commutative property. Commutative has the root commute. The word commute means to move. So the addition example would be if you have two numbers being added, a plus b, you can flip-flop them and add them in the opposite direction. Multiplication is also commutative. A times b is the same thing as b times a. You can move them. Associative property. The root word of associative is associate. And what you need to think about with associative is what's being associated together. And here's what I mean by that. Here, a plus b is being associated with each other because they're in parentheses. Parentheses are associations. So if you have a plus b plus c, again, the addition example, you can reassociate this and you could put the b plus c in parentheses instead of the a plus b. So you can change. Notice the order of the numbers did not change. A, B, and C, A, B, and C. If the actual order changed, then it would be commutative. The multiplication example, a times b being multiplied by c is the same thing as a being multiplied by b times c. You can change associations there. The identity property, okay, think if something keeps its identity, that means it stays the same. If you take a number, in order for it to stay the same, you could add 0 to it. Anything plus 0 is equal to itself. Anything times 1 is equal to itself. So that's your identity property, and these are what's called your identity elements. The identity element for addition is 0, for multiplication is 1. The inverse property, if you add something to its inverse, a plus negative a. Anything added to its inverse gives you the identity element again. We talked about what the identity element was up here. So anything plus its opposite is equal to 0. So what about multiplication? Anything times its reciprocal, that's the opposite for multiplication, is equal to the identity element. You could also say a over b times b over a is equal to 1. Inverses, when you're talking about multiplication, another word that we throw in sometimes is the word reciprocal. Reciprocals are the same thing as multiplicative inverses. Then finally, the distributive property says if you have a value being multiplied by a sum, that you can distribute that a. You can do a times b, and you can also do a times c. So it'd be a times b plus a times c. Now, this is not in this section, but I want to go ahead and throw in another distributive property that we always leave out. If you've got two things being added and then it's divided by something, this is also the distributive property. You have two things, a plus b, being added together, and they're both being divided by c. You can also distribute division. This would be a divided by c plus b divided by c. So you can divide them both by c, and that is legal as well. So next up, let's name the properties. We have 5, 2, and 8, 5, 2, and 8. Notice the numbers did not change. It was the associations that changed. So that would be the associative property. Associative. Let me zoom in so I can write a little bit better. Number 14, you multiply both of these by 6. So that would be your distributive property. Number 15, anything plus its opposite is equal to the identity element. That would be the inverse property. It'd be the additive inverse property if you'd like to add that to it. 3a plus 2b, 2b plus 3a, you moved commutative property of addition. And if you move them, you still have the same value. It's still equal to the same thing. Here you have x squared 8x1, x squared 8x1. You did not change the order of the values or the order of the terms. You simply changed the associations. You group different things together. So again, that would be the associative property of addition. Multiplying something by its opposite or reciprocal would be the inverse property. If you multiply something by its inverse, you get the identity element 1. This is still the distributive property, just backwards, 3 times m, 3 times n. Now later on, we'll talk about and remind you that the distributive property in reverse is called factoring. So that's actually a factoring problem there. And anything plus its identity element plus 0 would be itself. So that would, it kept its identity by adding 0. So therefore, that'd be the identity property. Okay, name the additive and multiplicative inverse for each number. Okay, the additive inverse, again, anytime you're talking about additive inverses, it's simply the opposite. So additive inverse of -8 would be +8. The multiplicative inverse, again, is simply the reciprocal. So that'd be -1/8. Again, to reciprocate a whole number, make sure you put it over 1. Additive inverse for 2/3 is -2/3. Multiplicative inverse would be the reciprocal, 3/2. The additive inverse for +6w would be -6w, because when you add them, you get the identity element 0. The multiplicative inverse would be 1/6w. Again, just flip it. And 24, the additive inverse of √10 would be -√10. The multiplicative inverse, since this is over 1, would be 1/√10. Now later on, we'll talk about rationalizing. We don't like that root being on bottom. We'll talk about later how we can get that root off the bottom. Okay, closure. It says a set is closed under an operation, and usually you're going to either say this is closed under addition, or this set is closed under subtraction, it's closed under multiplication, or so on and so forth, if the operation always produces an element of the same set. If an element outside of the set is produced, then the operation is not closed. So closed versus not closed. Now let's show you what we mean by this. Integers. Now first off, if you don't remember integers, that's like -3, -2, -1, 0, 1, 2, and 3, ... on each side. So those are all your integers. Are integers closed under multiplication? What does that mean is, could I take any of these integers, could I take any of these values and multiply them, and it's going to give me another one of those values? If you multiply -3 and -2, it's going to give you +6. Is that an integer? Yeah, it's over here. You multiply 0 and 1, it gives you 0. Is that an integer? Yeah, it's right here. If you multiply 2 and 1, does that give you another integer? Yes, 2, it's right here. So integers, since there's no way you can produce something that's not an integer by multiplying, is yes, closed. So that would be true. It says if it is false, give a counterexample. So now let's do irrational numbers. Irrational numbers are, again, values like pi, e, the square root of 2, the square root of 3, the square root of 5. Now the square root of 4 is not an irrational number because it's 2. So our irrational numbers closed under subtraction. Okay, let's use the most famous one, pi. What if we took pi and we subtracted from it pi? Anything minus itself is 0. So the question is, are irrational numbers like pi closed under subtraction? Meaning, if I subtract two irrational numbers, will I always get another irrational number back? And here, I subtracted two irrational numbers. Now, it happened to be the same one, pi minus pi, but still, any irrational numbers, can I subtract them and always get another irrational number? 0 is not an irrational number. So you took two values that were both irrational, subtracted them, and you get a value that was not irrational. So therefore, is it closed under subtraction? No, it's not. False. An example of that was what I just said. Pi minus pi is equal to 0. You could actually subtract any, you could do the square root of 3 minus the square root of 3. Both of those are irrational numbers. However, when I subtract them, I get 0. So therefore, it would not be closed. Whole numbers. Okay, your whole numbers are 0, 1, 2, 3, dot, dot, dot. Are they closed under division? Meaning, could I take any of these two numbers and divide them? Let me give you an example, like 2 and 1. Could I divide those and always get another whole number back? 6 is a whole number. 2 is a whole number, so 6 divided by 2 is 3. Yeah, those are whole numbers. That's a whole number, but there's a problem. Actually, a few problems. What if I took the value 2 and divided it by 3? Both of those are whole numbers. But if I do 2 divided by 3, that's not a whole number. That's 0.6 repeating. So, no, false. Whole numbers are not closed under division because of things like 2 divided by 3 is not a whole number. Here's another big example. 4 divided by 0. Division by 0 is undefined. You can't divide by 0. And since both of these are, finish writing that. Since both of these are whole numbers, then I should be able to, if it's closed, I should be able to divide them and get another whole number. I don't. Number 28, odd numbers are closed under addition, which means could I take any odd numbers, 3 and 5, and add them together, closed under addition, and get another odd number? No. No, and that first one actually worked out to be a counterexample. But let's look at all of them. 1 plus 7. Oh, that's still even. 3 plus 11, 14. Actually, it's right the opposite. If you add two odd numbers together, you never get another odd number. So are they closed under addition? No. False. And just give one of those as a counterexample. 3 plus 5 is equal to 8, which isn't even. So obviously they're not closed.